Welcome students, welcome to the next session of Strength of Materials 1. So in the previous class we have started our chapter which is deflection of beams, where we have calculated slopes and deflections of different beams, and we have started with our basic simply supported beams which are being subjected to point loads and UDLs. Now I am going into the next method which help us to calculate slope and deflection for the laborious and lengthy problems and a combination of loads also. Okay, so it is very laborious to solve eccentric point loads. Yes, for the simply supported beam having a point load at center and UDL over entire length, for such things itself we have got this much lengthy answer. That's why for making the lengthy process short, we are getting some more methods to make it simple. Okay, there is a convenient method for determining the deflections of the beams subjected to different loading combinations, and that was given by M.H. MACAULY. So based on the scientist name only, we have given the method name as MACAULY'S method. Okay, so for evaluating slopes and deflections for the different types of beams and calculating for the different combination of loads, it is very easy using the MACAULY'S method. So further, I am taking the example how they have mentioned. I am taking a simply supported beam with eccentrical load. So eccentrical load means simply a point load which is not at the center, some other position than the center line. So deflection of a simply supported beam with eccentric point load. Okay, a simply supported beam AB of length L and carrying a point load capital W at a distance small a from the left support and also at a distance of small b from the right support. So okay, in this way I have considered a loading figure, a simply supported beam having some cross section and length, and it is having a pointer W, and the point load is acting at a distance A from the left and B from the right support. Okay, and the overall length of the beam is indicated as L, and this shape, this dotted line is indicating that the deflection is occurring in the downward direction. As we already know, for the simply supported beams, our first output is needed to calculate the support reactions. As here also the same thing, we should have to calculate the support reactions for the eccentrically loaded simply supported beam. But how we will calculate them? Using sigma V is equal to 0 and sigma MA is equal to 0. As our simply supported beam is having eccentrical point load, sigma V is equal to 0, which is RA, RB, capital W at a distance A and B. So RA plus RB is equal to capital W, and also one more equation I can use, that is summation of all the moments about any support is equal to 0. So about the support A, which is RB into L in the anti-clockwise direction, plus W into A, which is equal to 0. That's why I have got RB is equal to WB by L, and RA is equal to the total load, what is W minus WB by L, and with this you can write W into L minus WB divided by L, and L we already know that is equal to A plus B, right? So this L I am replacing as A plus B, that's why W into A plus B minus W into B divided by L, and we have got W A by L as the reaction answer for and this is WB by L and that one is WA by L. Okay, so the values these are the support reaction evaluation. Now I am going into the main step. So we said double integration method is lengthy than the MACAULY'S method, and also we have said we can go for number of combination loads at a time in the MACAULY'S method. How? What is the main step? Even in MACAULY'S or in the double integration method, the first step is taking bending moment at a section. Okay, bending moment at a section, and that you should have to equate it to the original EID square over dx square. Okay. Now, the bending moment at any section, but here, see here, how many spans were there? First equation was there and also next equation was there. So, mx for the first span, one more step and completion. And then mx for the next span, again equating it to EID square over dx square. So, in case of double integration method, first I should have to take in between A and C one section. The corresponding mx, I should have to equate it to EID square over dx square. Again, in between C and B, we should have to take one more section. Again, that mx should be equated to EID square by dx square. So, two complete process needed to be completed for evaluating the overall structure's one answer. But in case of MACAULY'S method, at a time I can do, and how we will do, now we will see there. Okay, see here, the bending moment at any section between A and C at a distance x from A, which is given by mx is equal to so, the bending moment at any section at a distance x from A is given by WB into L WB into L into x, RA into x. So, that bending moment equation WB by L into x. And next span, when we consider any section line at a distance again at a distance x from A, but after the C point. Now the corresponding mx equation is RA into x. See here, RA into x minus W into x minus A. Okay. So, for the next span, mx is equal to so this one is RA into x, and the next thing RA into x minus W into x minus A. Okay, so this is the way we are writing the bending moment at a section. Now, in these two terms, see here, first thing WB by L into x. Here also the first term is WB by L into x. So the first term is common. Now, the main step involves here only. The above equation BM holds good for the values between x is equal to A to B, A and B, and the BM for all the sections. So, this is from 0 to A. This is from A to B. So, the above equation holds good for 0 to A. Starting from 0 up to A, the above equation good. And then from A up to L length, the remaining equation is good. Okay. Now, I am writing the next equation as the main reference and writing as mx. But, how much is the first portion? Up to the right and give the vertical dotted line. WB into x by L with a vertical dotted line, and from this equation whatever is the leftover portion with as it is sign, I will write here minus W into x minus A. And now stop that dotted line. Okay, stop at the dotted line for the any point in any section, but for any point in the section CV at a time I can implement. When you want to see up to C, from A to C, when you want to calculate any bending moment, you should have to observe in between these. Okay, so from A point to C point, when you want to calculate any points, deflection, section, slope, anything up to the first dotted line, you should have to observe. But when you are taking any point in between C and B, from the first up to the second, nothing but the whole equation you should have to consider, not the left part. From the first up to that position I should have to consider when you are considering from C to B. Okay, this is up to 0 to A. Okay, again from A to L we should have to consider, or A to C, this is okay. In between C to B it is considered. When any point is considered in between A and C, up to this equation okay. When any point is considered in between C and B, I should have to consider this equation up to this part. Equation up to this part. Okay, stop at the dotted line at any section. Okay, Next, the benevolent section, we have got the formula which is EI d square by dx square. Now, that EI d square by dx square is equal to as it is WB by L into x dotted line minus WX with x minus A. And we already said the integration process, everything is as it is, but at a time 2 spans I am doing here. For the double integration, separate integration, again separate integration for the next spans equation. But here at a time with a simple dotted line separation, integrating at a time. Okay. When you need to consider up to the first dotted line, we will consider the first dotted line. When you need to consider the next section, we will consider the whole equation. Okay. Now, integrating the whole equation as it is, the dotted line is continuing, we are integrating whole. But remember one more thing, when you are integrating, the integration constant should be added before the dotted line for the first equation itself. So, the integration constant should be added before the dotted line. So, here we have got the equation and the first integration will give EI dy by dx, and with the integration we have got, so which is the benevolent section EI d square by dx square. So EI dy by dx, we will get that WB by L into x square by 2 plus C1. Just now only we have said the integration constant should be added below the dotted line. Again, the remaining parts as it is will be integrated. X power of n by n plus 1 or anything function, the corresponding function, and its integration will be done. And again, next integration. So, for the same section, when we go into the next integration, we will get EI into y, WB by 2 into x cube by 3 plus C1x plus C2. Again, the dotted line indication, the next function's integration part we are writing like this. So, in this way, the slope equation and deflection equation with the integration constants we have completed. And in the last step only we have said, up to the first dotted line means when you are considering any point in between A and C. Once you are considering any point between C and B, you should have to consider the whole equation. Okay. Now, where the C2 is another integration constant, the constant is written after C1x. The integration of x minus a whole square will be x minus a whole cube by 3. This type of integration is justified as the constant of integration C1 and C2 are valid for any value of the x. Okay. The value of C1 and C2 are obtained from the boundary conditions. The two boundary conditions are at x is equal to 0, y is equal to 0. And x is equal to L, y is equal to 0. And also, you can use these two boundary conditions for evaluating the two answers. And x is equal to 0, where it is located? That is located in the first, in between A and C. So, how much of deflection equation I should have to take? I should have to consider up to the dotted line only. Yes, in the deflection equation, at x is equal to 0, y is equal to 0. Substituting these values in the deflection equation up to the dotted line. Okay, substituting that answer only we will get C2 is equal to 0. Next thing, at x is equal to L, y is equal to 0. Where it is located? It is located in between C and B. So, what we should have to do? In the deflection equation, the complete equation needed to be considered. So, at x is equal to L, y is equal to 0. Substituting these values in the equation, we will get 0, the corresponding substitutions, C2 substitution, and C1 is the only unknown coming out. Okay, C2 is substituted and C1 is the only output coming. So, after substituting in the main slope equation and deflection equation, this is C1 and C2, we will get C1 answer and C2 answer like this, and substituting C1, you have observed EI dy by dx like this. So, this is my slope equation. Okay, this is the slope equation. And then substituting C1 and C2 in the next, we will get the deflection equation. But, and in the slope equation, what I can say? So, we have already said the slope equation is giving slopes of different points where you want to calculate the slope. Okay, and how you should have to refer? As I have calculated the measure from the left section, so that point also should be measured from the left. So, from the left, what is the distance of particular point? If I want to calculate the slope at A, so that distance is x is equal to 0. So, at x is equal to 0, dy by dx is replaced with theta A. Okay, from the slope equation I am calculating that part. Okay, and also in the whole equation up to the dotted line only we should have to write. Why? Because that is in between A and C only. Okay, so from the equation up to the dotted line only I am writing because the A point is in the first span only. Later also I am considering the whole equation, but that is referring CB spans answer. Considering the whole equation will give CB spans answer. Considering up to the first dotted line will give AC answer. Measurement starts from A but consideration in between C and B. Measurement starts from A, but considering between A and C. In this way, we have got theta A answer. And the next thing is calculation of theta. Next one, deflection answer. So after substituting C1 and C2, we can evaluate deflection equation. And also, in the deflection equation, what is the thing you can generate? In the deflection equation, what you can say? We can calculate deflections at different points. Yes, once you want to calculate deflection at the loading point, nothing but from the left support, the loading point is at A distance. That's why. So, from the left support to the deflection loading point, that is x is equal to A and y is equal to, so EI into YC. Only I have given, that may or may not be maximum. Just under the load, I am calculating the deflection. Under the load only I am calculating the deflection, and I am not indicating it as maximum. Why it is not maximum? For any load which is being symmetrical, the deflection is maximum at the center. That was a standard condition. But here no such type of conditions were there. Simply I am calculating deflection at C point. So EI into YC is equal to the corresponding deflection equation and substituted with the corresponding x value. Okay, so this EI into YC, and I am substituting the corresponding x value from the left support, and I am calculating the deflection answer, and we have got minus W A square B square by 3EIL, as this minus again indicating the deflection is occurring in the downward direction. Okay, so that y is equal to 3A square B square by 3EIL at the loading point. So, in this way, we can evaluate at a time. But in case of double integration, what we should have to do? In case of double integration, first span mx equation, we should have to equate it to EI d square by dx square. Second span's mx equation, we should have to equate it to EI d square by dx square. Overall integrations, boundary condition substitution for that particular span only, overall consideration, and will give theta A, theta B's and the corresponding deflections at those points. But in the MACAULY'S, at a time, different eccentrical loadings, combination of loadings at a time will be evaluated by separating with a dotted line. Span to span, dotted line indication will be there. Okay, now I am going into a numerical, how we will solve a problem for the MACAULY'S method. Okay, so a beam of length 8 meters is simply supported at its ends. It carries a UDL of 40 kN per meter as shown in the figure. Okay, a beam of length is there which is simply supported and carrying a UDL of 40 kN per meter over the UDL, but not they have mentioned that is entire length. They have shown the figure itself. Okay, so from the left support up to 1 meter no load is there. Later the load has started. Again it has stopped after 4 meters. Again the remaining 3 meters was left. Okay. And the sections Young's modulus and moment of inertia they have given, because in the deflection we are using EI, right? WA square B square by 16 EI or WLQ by 48 EI, 5WL power 4 by 384 EI. In that way, E into I is involved in the deflection calculation and flow calculation. And that E into I multiplication we call it as flexural rigidity of the section. So, E into I multiplication we will do. So, that E into I multiplication is important for calculating slope and deflection. If not, we can keep E into I as it is. If they have mentioned, we should have to substitute with the proper units. Okay, so this is the loading figure. As we have already said, for the simply supported beam analysis, we should have to calculate the support reactions. Okay, I want to calculate the support reaction. Simply I am writing the given data. Whatever is the length of the beam, whatever is the intensity of the UDL they have given, and what is the Young's modulus, what is the moment of inertia of the section, and also I need to calculate the reaction at support A and reaction at support B. Okay, RA into 8. As it is, whatever is the loading you are having, that load's moment only I am writing. Okay, so for this section, what is the moment equation? Sigma MA is equal to MB is equal to 0. So I have got RA into 8, which is clockwise, and minus 40 into 4 into, with respect to B, it is at how much distance? Up to this is 2 meters, and then this is 3 meters. So 4 into 5, 3 into 5, 4 into 5, 40 into 4, and from the center load acting point to the B point, that is 40 into 4 into 5. So this is the UDL. So in this way, we are writing bending moment about B is equal to 0. So RB into 8 is equal to 40 into 4 into 1 plus 1 by 2. So we have written with respect to RB sigma MA is equal to 0. That's why RB into 8 anti-clockwise plus 40 into 4 UDL, and it will act at this distance with 1 plus 2. Why it is 2? Because out of 4 meter length, at the center only the load will act. From the center to the RA support, that is 3 meters. So 40 into 4 into 1 plus 4 by 2. So that step only they have written, and which I should have to make equal to 0. After making equal to 0 only they have given in the equation. So that is RB into 8 is equal to 40 into 4 into 1 plus 4 by 2, which is 480 kilonewtons. So RB answer we have got 60 kilonewtons. Once you are getting RB answer, I can calculate RA answer. Yes, the total upward force is equal to the total downward load. The total downward load is 40 into 4, and the upward force are RA plus RB. Once substituting RB answer, I can evaluate RA answer, which is equal to 100 kilonewtons. Okay. Now, before entering into the analysis step, okay, I have calculated RA. But for writing the MACAULY'S equation, what we should have to do? The terms one by one, the terms should involve the first parts. So, once I am writing up to first span, what is the bending moment equation? The corresponding equation I will write. And writing the next equation, I will write the next equation. But when I am writing the next equation, these two terms will be involved. Some other terms should be added, right? So, whenever the span I am considering, the first two terms I am using. First term I am using in the second equation. That was the first term of the second equation, and some part is there. Similarly, when I am going for the next equation, these two terms should be there. Some other also should be there. That's why I am adding. Okay, in order to obtain the general expression for the bending moment at a distance x from the left hand, which will apply for all the values of x, it is necessary to extend the UDL up to the support B with equally upward and downward loads. Okay, with equal and upward and downward loads, I am adding the UDL. Why I am adding this UDL? Because see here is we are getting RA value, and then we are observing the MX equation for AC. Simply observe this term, MX equation for AC, which is equal to RA into X, because up to this section line I have considered the X. So plus RA into X. Next, MX for CD. When we are writing MX equation for the CD, what is the MX equation? That is plus RA into X. Okay, plus RA into X. Again, minus 40 into how much it is left? That is X minus 1 length left. So, this portion length is X minus 1, because that is 1, no UDL is there. And also, from the center, this load may act. So, at a distance of X minus 1 by 2. So, in this way, the bending moment for the CD we can write. And for dV, MX for dV is equal to, see here, if this loading is not there, okay, only it was empty. So only this UDL is there, minus 40 into 4 into how much it is there? It is spread up to this length, and from the center to this measurement I should have to write the perpendicular distance. Yes. So where it is? Now from the overall length of x, how much I should have to remove? This perpendicular distance only I should have to write. So from the center point of this, where it is will be located? It will be located at total x minus 1 minus 2. So at a distance of x minus 3, the force will be indicated. See, 40 into 4, that UDL is acting at some point. From that point to that distance is x minus 1 minus 2. So that is the perpendicular distance. So see here, when you observe, for the MACAULY'S, dotted line separation is indicating the whole equation at a time. See here, when that UDL is not there, only the original condition is there. The first part, okay. And for the next part, yes, you can write dotted line like this and you can write that. And then for the third part, okay, the first part is there. And the second part should be there. Involving the second part, some more part can be added. So that is for the third span's answer. But here, these two terms are differing. So to continue or to get the general equation, I should have to add the continuous downward UDL over the remaining length, and also how much length I have added the downward UDL. In the same length, I should have to apply the upward UDL. Why so? So that this equation will be continued here also, but also some other term will add after this point. This equation generally continued. Okay, so whether it is continued or not, now we will see. See here. So, firstly, we are considering the first section and writing like this. And I have applied the UDL like that. Okay. Now I am considering the section line here. First section we have taken here and the next section we have taken here. Now I am taking the next section line here after applying the upward UDL and the downward UDL. Span. After applying the downward UDL and upward UDL, first next write the bending moment equation for the dB span. Okay. So what it is involving? It is involving plus RA into X. See here, it is involving plus RA into X. Okay. And then it is involving a UDL of how much length? Downward UDL of intensity 40. It is having a UDL of intensity 40 up to this level. Okay. It is having a downward UDL of intensity 40. And how much length it was spread? Overall x minus 1. That's why x minus 1 it was spread. And where it will act? Out of this x minus 1, at the center it will act. The remaining perpendicular distance I should have to write. And that one is x minus 1 by 2. That was the term only for the downward UDL. Now, after this point, there is an upward UDL, right? So, I should have to write for the upward UDL. Yes. So, it is causing the upward movement. That's why, again with a 40 intensity. And what is the length of this UDL? This length of the UDL is x minus 5. Again, this x minus 5 length of UDL will act at the center. So, from the center to this distance, which is x minus 5 divided by 2. Now, see here, why I have said generalized term. Okay, when you observe the first term, I have got plus RA into x. And observe the next span, RA into x. Along with that, I have got minus 40 into x minus 1 into x minus 1 by 2. When I go for the next span, R minus RA into x. Okay, and the next term as it is came, see here, minus 40 into x minus 1 into x minus 1 by 2. Involving this, some more term I have got. This is plus 40 into x minus 5 into x minus 5 by 2. So, involving 3 equations in a single equation, I have got the last equation. But how it is involving? When you want to consider the first span, I should have to write up to first. Or when you want to consider the next span, I should have to observe the equation up to next. When you want to observe the last span, I should have to write the whole equation. So, span-wise separation is happening in the same bending moment equation. Now, that answer I am writing here. So, this one, EI d square by dx square bending moment at a section is equal to RA into x. What we have got here just now, RA into x. And then, minus 40 into x minus 1 into x minus 2, x minus 1 by 2. Yes, minus 40 into x minus 1 into x minus 1 by 2. Again for the next span, plus 40 into x minus. Why it is plus? Initially that was downward load. So, the downward load is causing this movement. But this one is upward load and causing the positive type movement. That's why 40 into x minus 5 into x minus 5 by 2. And with this, just a simple multiplication and substitution I have done without nothing. Okay, EI d square by dx square is equal to 100x minus 20 into x minus 1 whole square and then plus 20 into x minus 5 whole square. And for the first integration, you can evaluate EI dy by dx, which is equal to 100x square by 2 plus 7. As we have already mentioned, the integration constants should be added below the first dotted line. The integration constant should be added below the first dotted line, 100x square by 2 plus 7. And separation with the dotted line. And integration of this function, n for n plus 1 by n plus 1. And then integration of this function again n plus 1 by n plus 1. So, this we have got an slope equation with the integration constant. And the next integration, we can get the corresponding second integration constant, that is EI into y. As it is integrations, but C1x plus C2. Again, the next term's integration, the third term's integration. Not every term should have the integration constant. For the whole equation, C1 comes and that C1 I should have to add in the first. Again, for the whole equation, C2 comes in the next integration. That C2 also I should have to add in the first term only. Okay. As you already know, the integration constants should be evaluated from the boundary conditions. Here also I am doing the same. So, the C1 and C2 constants of the integration, their values are obtained from the boundary conditions. What are the boundary conditions I am having? Being it as a simply supported beam, I can say at the simply supported end A, at the simply supported end B, the deflections are equal to 0. Yes, at x is equal to 0, y is equal to 0, and at x is equal to 8 meters, y is equal to 0. So, x is equal to 0, y is 0, x is equal to 8, y is 0. But, substituting x is equal to 0 and y is equal to 0 in the deflection equation, up to which part? Up to the first dotted line only. First dotted line and second dotted line. Like that we indicate, and up to the first dotted line only I should have to indicate the first boundary condition. So, x is equal to 0 and y is equal to 0 indication. And going with the main equation up to the first dotted line and substitution will give the main answer of the integration constant, which is C2. And then substituting C2 back in the main equation and taking the next boundary condition. What is the next boundary condition? That is for the simply supported beam and having the load variations and having the separation, I should have to observe the next boundary condition only with x is equal to 8 meters and y is equal to 0, observing the up to last point. So, the whole equation of deflection equation needed to be used. So, the whole equation of deflection equation will help us. See here we have got the whole deflection equation, and substituting the whole deflection equation, you can get this answer, which is 0 is equal to substitution of the x is equal to 8 answer. With the arrangement, you will get C1 answer. So, C1 answer and C2 answer will be evaluated. These integration constant substitution in main slope equation and deflection equation will help us for calculating the next answer. So, I am calculating deflection at the center as they have asked in our problem. So, what they have asked? I should have to calculate deflection at the midpoint of the beam. I should have to calculate the maximum deflection position, and also I should have to calculate the maximum deflection answer. Yes, simply indicating overall 8 meter length and center. So, overall of 8 meter length center, where it is located? It is located in between C and D. So, for using the C and D span, I should have to use the second. So, after first dotted line, the second segment is there, right? So, up to the second dotted line, I should have to take the deflection equation, and the corresponding equation only will help. Okay, then the position of maximum deflection and the value of maximum deflection, where it will occur? So the position of maximum deflection will be at a point where the slope is equal to 0. So where the slope is equal to 0, I can calculate that. Okay, substituting x is equal to 4 up to the first dotted line, you will calculate y corresponding answer. Simply substituting our Young's modulus and moment of inertia of the section. So from the deflection equation, this answer will be evaluated. Again, position of maximum deflection, how it will be evaluated? We have already said the point with maximum y, it will have slope is equal to 0. Why it is a basic mathematical condition only. When y is becoming y maximum, the corresponding dy by dx should be equal to 0. So y is our deflection. We want y deflection to be maximum and the corresponding slope dy by dx should be equal to 0. Okay. In this way, I am considering the position where this thing happening. So where the slope is equal to 0, that will give the position for the maximum deflection, right? So the position of maximum deflection will be located from that and the corresponding x will be substituted again back in the deflection equation, will help us for the evaluation of maximum deflection answer. Yes. So see here the position of maximum deflection. The maximum deflection is likely to be happened between C and D, so that the dy by dx for the CD span I am making it equal to 0. So from the equation, the CD span, the deflection equation I am making it equal to 0 and substituting we have got x answer as, so the corresponding x answer from the trial and error method, and finally we have finalized at a distance of 3.83 meters. In between 3 and 4, I am getting the maximum deflection. With a number of numericals, you can get the same answer. So from 1, 2, 3, like that I am evaluating, and finally where the deflection is becoming maximum, nothing but the slope is becoming 0, that location we have got 3.83. At this 3.83, I am again calculating the corresponding deflection. Substituting the 3.83 answer in the equation, you can evaluate y maximum. So this y maximum is equal to the corresponding output, but in the negative condition. Why it is in the negative condition? In the previous step also we have mentioned, as the deflection is going in the downward direction, so the negative will be coming, but negative indication is not in anything. Originally the beam is going like this, so downward y will indicate it as negative. So the deflection we can indicate as 16.33 mm at a distance of 3.83 from the left side. So at x is equal to 3.83 meter from left, the corresponding y is equal to 16.33 mm in downwards. So in this way we have evaluated the maximum deflection position, maximum deflection value, and also calculated deflection at the center. Okay, in this way we have completed this numerical, and in the next class we are going into the next concept.